Hello everyone. So we'll start today's session. We'll be doing some questions. We'll solve some questions related to week 5 content, that is regarding root locus. And someone has asked regarding this week 4 solution, which has not been uploaded on NPTEL portal. So that will be uploaded by concerned authority. We don't have any access to that, so I can't say. Like TS don't have access to that. Okay. Okay, fine. So let us start the session. So this is the first question, and it says that there is a unity feedback system with GS. This GS means the plant in the feed forward path. So we have a system like this, and suppose there is a gain K. So with variation in K, how the roots of this closed loop system varies, that we have to see. For that, there are number of questions that we have to solve related to this one, like how root evolves with variation in K. So first one is the angle of asymptotes. So if we see this, we know for root locus, we have to deal with the characteristic equation. So if we see the transfer function, it is G by now this denominator we have to deal with. So 1 plus kg equal to 0. This is the characteristic equation that will define how the roots will evolve. And to in order to show the evolution of poles, we know that like for root locus, we have to satisfy this criteria, that is kg equal to 1, sorry, minus 1, because this will go on that side. Now this g, it is a function of s. And this s is a complex number. So we can say that this is a complex number. Therefore, means for every complex, suppose x, I, j. So we have this kind of representation that we represent it by x square plus y square, and then angle, that is tan inverse y by x. So this kind of polar representation, this is rectangular representation. So generally when we say that, so suppose for this one, there are two roots, 4 plus j4, I think yes, minus 4 plus. So this is kind of rectangular representation of complex number, and this also we can represent with angle. Now to satisfy this criteria, so we can write in terms of magnitude and the phase angle. So this will be one, and angle of this one should be plus minus 180. Okay, so based on this, there are different like set of rules that were defined in the lectures to find the root locus. So to find the asymptote, now here the number of roots are 4. So there are 4 roots. One is at number of poles of this transfer function, or we can say the root of the characteristic equation is 4. And these poles are at 0, -4. And what is the number of zeros? This is 0. So that means 4 minus 1, that is, suppose this is n, this is n. So n minus m poles will evolve and approaches infinity. Okay, now approaching infinity, that means it has to follow some path, and that was defined by this asymptote and the centroid, like finding centroid, how this will evolve. So it will evolve along the asymptote. So we have to find the angle of that asymptote. In that case, we know that if we have to find the angle, we have this formula, this 80 by n minus 1, which is 4. And here k varies from 0 to 3. Okay, so what will be the angle for this one? So this will be 2k, no? So that it is odd. 4, so phi a will be 45 degree, 135 degree. So this is what we get as asymptote angle. But apart from this, we also have to find the centroid so as to draw the root locus. So this is the next part, or we can say next question, which is the center of asymptotes. So for that, again, we have this formula that this center of asymptote, we can write sum of real parts of the pole. Here I is equal to 1 to 4. You can say here there is a 0, so we don't have to say. So this is going to 0 because there are no zeros, and this is n minus n. So this will be 0 since poles are at 0, -4, and these two conjugate poles. So here we have 0, -4, -4, -4 by 4 minus 0, which is -3. Okay. So that means if we see the S plane, that is sigma j omega, we have one pole here. So at approx this -3, we have asymptotes which are like at 45 degree. This angle, then this line, and then this line. Okay, this much we know. Now, on the real axis, we see, if we see, so this line, because this is one pole which is to the right of this interval. So one pole, that means it is contributing to like odd number of poles and zeros, then it contributes to this phase angle of the locus. So we can say that this one is in the like root locus will lie, some part of root locus will be here, means root will lie in this region also while evolving. So this much we know. Okay. Now, since there are four poles and no zeros, that all poles are going to infinity. So we have to find the way how it goes to infinity. So for these two poles, there should be some breakaway point, we can say, so that it goes to infinity. Then we have to find that. Also, for this angle, we'll have to, sorry, this for these two poles, these complex conjugate poles, we will have to find the departure angle so that we can find how the poles will evolve. So the next question is to find the breakaway point locations for this one. So for this, what we'll do, we have the characteristic equation. One plus k g. G is plus 32. This will go to 0. So this denominator of this one will multiply by 0 will be 0. That means this is equal to 0. Now this is the characteristic equation. We will simplify this one and we'll try to find the value of k. So just simplify this one. This will give s to the power 4, 12s cube. Okay. Now what we have to do? We have to differentiate this k by with respect to s. So this is minute 4s cube. This 4 plus 128s plus 120 equal to 0. Now, since this is the condition, for this one, we have to find what is the value of like roots of this equation. This third order quadratic equation, either you can write it in MATLAB that these are the this is the coefficient of polynomial and find the uh, roots of this will means we try to write it. Let us see. Is P minus 4 minus 36 Okay, so this is the answer. is visible. Increase the font size. So these are the roots of this equation. Minus 3.7. Point 0.53 and minus 1.577. Okay. So this we know that minus 1.577 is on the root locus, because we have seen that this part, this real part of real axis is in the root locus. And about this one, this minus 3.77 something, so it will be approx this one at this point, at this point. So these points are not in root locus. We'll see also when we try to find the angle of departure, that we can put this value and find out that this doesn't satisfy the angle criteria and the magnitude criteria. Okay, so this one is the breakaway point. That means if we go to root locus, this S-plane plot, somewhat here at this point, minus 1.57, the root, these two roads are coming, and then from here it will break away. So we know that these roots will proceed towards this, like along these asymptotes. So that means it will go like this, these two. Okay, so about these two roots, we know that these will evolve like this. For these two complex conjugate poles, we don't know. So we'll see that also. But if you see that as we are increasing the gain K, when gain was 0, poles were there on closed loop poles. But as it increases, these poles are evolving and it is crossing this imaginary axis. That means it is going in right half S-plane. So if we increase the value of K, which is at this point, suppose K star. If K is greater than K star, then the system becomes unstable. This system, this closed loop system becomes unstable. So we'll try to find out what is the value of this critical value of this gain. This is the next question. So we know that root locus is crossing j omega axis and we have to find the value of K. So for that, what we'll do, we'll just, because it is crossing j omega axis, so we have seen Routh-Hurwitz criteria earlier, that we try to find the, like, analyze the stability of system using Routh-Hurwitz criteria. And there also we say that, okay, if in Routh-Hurwitz criteria or Routh table, we find some auxiliary equation, that means that the roots are on the j omega axis. Some of the roots are on j omega axis. So we have this characteristic polynomial, this one. Plus 64s. This is the polynomial. Okay. So we'll create a route table. One, zero. We'll just cross multiply these two and divide by 12. We'll get 160 by 3. And this will give k. Now if we do this, this will be here and this will be 0, 0. And then again, if we multiply this with this one, and this will be multiplied with 0 divided by this will give k. Okay. So since the roots are some of the roots are on imaginary axis, that means this one, this row elements should be 0, all the elements. That means this is 0, this is 0, and this should also be 0, so that we get this auxiliary equation, That means this should be equal to 0. Now, if we equate this one, we get k equal to something, yes. So this is the value of k at which this root locus crosses the imaginary axis. Now, if gain is increased above this value, then this closed loop system will become unstable. So for this root locus, this k star is okay. Now we'll see how these two poles evolve. So we'll try to find out the departure angle of these two conjugate poles. Okay. So if we see some value, or we can say some point close to this pole, so what will be the angle contribution we have to see? Let's suppose that this one we write as P, this pole, so theta P plus angle contributed by, can say S, suppose this point is S. So S minus 0 by this one. What is the angle contributed? Then As these are the poles. Then angle contributed by this one. Now this would be plus minus 180 approx. Okay, so theta p we can say that is minus theta net. What is the theta net? So since there are no zeros, then we have this one. So this will go this side, it will be negative. And this will be by this one. We have 4 by 4. And this is on this side. So this angle will be 45 degrees. So it's 135. So this is 135. And then we have, because of this, we have 90 degree. For this also, we have 90 degree. So what will we get? If we take 180, so this will be this is 135 minutes. So this will be minus 135. Now this minus 135 means that it goes somewhat like this. You see, this is minus 135. Now if we compute it from this side, this will be 360 minus 125. So it's 225 degrees. That means this is going like in this direction with minus 135. So it is going like this, and we know that these two asymptotes are there along which the root has to evolve. So it will go all like this. So this is evolve. So now we have this root locus. So we can draw this using MATLAB also. Basically, we can get, obviously, MATLAB will give us all the results without all these calculations that we have done. But this is a good like thing if we know how this works, so that if there is some debugging or analysis has to be done, then we can interpret these plots and all given by this simulation tool. Okay, so what we have to see, what is the root locus for this unity feedback closed loop system when the gain k is varied. Okay. Acha. K was there also, so we don't need any gain. Sorry, I missed it. Okay, so this is the transfer function, or we can say since it is unity feedback, so we can say GH equal to G, and we have this open loop transfer function as K by S plus 4, S square plus 8S plus 32. Okay, so I shared the screen. Sorry. Fine. So we have to find the root locus for this plant, and K is varying. So we'll go through this command R locus. Let us see. We can do here also. Fine. So we have this command in MATLAB, which is rlocus. So if we type help rlocus, this will give all the description about this one, how this command work, what is the input to this one, and what will be the output of this one. So what it says that the input is a system, and it computes and plots root locus of CISO LTI model system. So since we are, as of now, we are dealing with single input, single output, because we are seeing only one input is there, means one dimensional, and then also output is also some scalar value. But later in this course, we'll go through a state space model, then we'll have this multiple input, multiple output LTI system. But as of now, we are concerned with this CISO system, and that is also LTI because we are dealing with transfer functions. So we can't define transfer functions. Like we don't have this concept of transfer functions for time varying system. Okay, so this is the closed loop system for which it gives the root locus. And it says that it shows a trajectory of closed loop post when feedback gain k varies from 0 to infinity. So the system that it shows is this k is in feedback, but here the system that we are having is k is in forward path. So does this matter? Like, will this change the way of analysis? And also basically no, because what we are considering is this characteristic equation. So when we see characteristic equation, this is always this g into, if this is h in feedback, then this will be gh. So we are dealing with this one. That means for this system where g is having this variable again k with unity feedback, or we consider a system with 1 by s plus 4, s square plus 8 s plus 32 with gain k in feedback, both will have same kind of pole evolution behavior because the open loop transfer function for these two, if we say gh, this will again be this one only. So these are same. So what analysis we'll do for this? This will be valid for this also. Okay, so we know this about root loop r locus command. So we'll apply this one. Now, if you try like want that root locus would plot the evolution of root for a specific values of k, then we can apply the value of k. Otherwise, it will take the value of k from 0 to infinity. Okay, so let us see what is the system. We have s plus 4 and this one. So for this one, we have to give system as input. So first we have to define the transfer function. That means system is here transfer function. So we'll see, we'll use this tf command. So let us see this tf command. This, what does it do? Okay, so there are various variants of this one. So this is one of the variant where we provide this numerator polynomial and denominator not polynomial, you can say coefficient vector, and then it gives us the transfer function. So we'll just use that one only. We had one equation as, you see this one, s plus 4. So what can we write this as? This will be s square plus 4s plus 0, and then multiplied with s square plus 8s plus 32. Okay, so we'll do this only. So we have s square, which is 1, and then 4s, and then 0. Okay. So we have this, and then suppose b, which is s square plus 8s plus 32. So this is 1. And in the denominator, what we have? We have multiplication of these two. So we have this conv command, which does this one. So we have A and B. Okay. So this will be the coefficient. Now this is 0, s to the power 0, s to the 1, 2, 3, 4. So this is like that. Okay. And in numerator, we have 1, because now we are seeing the analyzing this system. Okay. Or we can say this system basically same. So we'll say that in numerator, we have only 1. Okay. So we'll apply the transfer function command and we'll say that create a system with this numerator and denominator. So we have got this transfer function, which is a open loop transfer function, and now we have the variable thing is k. So now we'll plot the root locus with system as input. Okay, so can you see this? These are two poles. Here gain is 0, pole is -4, damping is 1. This is the second pole that we are having. Okay. Let us vary this point and let us see how it proceeds. See, gain is varying, gain is 37, and here the pole is also, pole location is changing gain. And this pole reaches here, and here there is this breakaway point, and then it goes away like this. Okay. At this point, so somewhat around this point. Okay, so it's 0 -0.0049. So if we increase this a little bit, then it will be 0 and we'll be having some imaginary poles. So at this point, gain is approx 566. So we'll increase little bit, we'll get 568.9 or something. And then after this, the system becomes unstable. So this is the evolution of this pole. The another pole goes like this. This pole also, this conjugate complex pole, we saw that the angle of departure is this 255 degree or -135 degree. So this will go like this. Okay. So this is the root locus of the system, which is given in the question. Now we'll see next question. Now, since we have done this, so last time we had one question. Where it says that the steady state error has to be kept some within some range, and we have to find the value of k for which we can achieve that one. This question. Then we found some value of k, we satisfy that, but we saw that using the Routh criteria, using this whole application of Routh criteria, we saw that it is saying minus k square greater than 0. So k square is always a positive number, and minus k square can never be greater than 0. It will be negative. Therefore, we saw that, like, we came to conclusion that this system is unstable and we cannot find value of k which satisfy this, like this performance cannot be achieved. So we'll see what we can like we'll also do this root locus analysis of this one. So how the root evolves for this system. So this is a feed forward path. We had d setting to 0, and then if we analyze this one, this is the variable, so we can consider this like apart from these whole thing. So we have gs, which is s plus 1 by s plus 3, s plus 2, and s square plus 1. Okay, and we have variable which is k. Now this is a unity feedback system. So what we'll do, we'll use this one and we'll see how the root locus is there for this system. And then we can verify that the thing, the conclusion that we draw from this Routh criteria, whether it is correct or not. So we'll just do this. Just clear the workspace. Then we have, now there was this command tf that we use. So since we have this poles and zeros specified here, so we can use other command also which directly uses poles and zeros value and gives us the transfer function. So we have this command which is zpk. Okay. So let us see what it requires and what it gives us output. Okay. So it gives a system which is transfer function and creates a continuous time 0 pole gain model with zeros j, poles p, and gain k. So for this system, we have gain as 1, poles at 3, minus 2, and plus minus j, and zeros at minus 1. Okay, so we'll create this. So we have z equal to minus 1, p equal to minus 3, minus 2, then I minus 1 star I. So I, we are denoting imaginary number. This is notation in MATLAB, so we can use I or J something. Okay. So these are the poles. And now gain that we'll set as 1. We'll say we'll call this function zpk. So gives us just the system, and we have z, p, and k. So this is a transfer function which is similar to this one. Now for this transfer function, we'll get the root locus. So can we see, since there was pole at minus 1, okay, so there was 0 at minus 1 and then there's pole at -2, -3, and these two imaginary points. You can see the complex conjugate poles. So for this one, for real axis, we know since this is one pole, the odd number of poles, so this part of real axis will be in the root locus, and this one will not be because there are one pole and 1 0 in right side of this part. So this will not be on the root locus. This one will be on the root locus. Now, since there is 1 0 and 4 poles, so 3 of the poles will go to infinity as k goes to infinity. So in that case, we need to find the asymptotes. So if we find the asymptotes, it will give some kind of 60 minus 180 and then some angle in this direction. So we can see one of the pole, which is this one, it goes to infinity along minus 180 degree. And these two will evolve like this along the other two asymptotes. And here we can see that these poles, like this, there are 4 poles. So one pole is always on in the left half plane. This pole is also in the left half plane and it reaches this point as k tends to infinity, which is also in left half plane. So these two poles are stable. But these two complex conjugate poles, as k increases, even for a small value of k, this is in the right half plane. So that means this is this system. Since there is one unstable pole, or we can say one right half plane pole, that means the system is unstable. This is what we had concluded last time, and from root locus, now we have verified this. Fine. So now we'll proceed to next question. So the next question. So this list one is the list of root locus, and list two is the list of transfer functions. Now we have to find which transfer function belong to which root locus. Okay. So what can we say about this one? Let us apply the concepts of root locus. So we have this transfer function, which is s plus 2, s plus 1 whole square. So we have two roots at -1 and one root at -2. So this part of real axis, since there are 2 poles here, so this will not be in the root locus. And for this part of the real axis, since there are 3 poles, -2, -1, -1, so this will be on the root locus. Okay. Now there are 3. Okay, this is 0. No? So this will be on the root locus. Fine. There is 1 0 and 2 poles. So one will go to infinity and one will reach this point. And for that there will be some asymptote. So for asymptote, if we try to find, this will give 180 degree. So it will be this axis. Okay. Now these two will break away because these two will go, one will go to 0, one will reach infinity. So we have to find this breakaway point and then we'll have to find breaking point. And if we compute this dk by ds, we'll get some point here. This will go like this. one pole will move to this 0 and one will go to infinity. So for this one, this is the root locus. Now if we see this one, since there are options, so we don't have to apply that much mathematics and draw the exact root locus, but from the steps we can identify, okay, this is the thing and it will proceed like this. We have 1 by s plus 2 s plus 1 whole square. So now we have three roots, so three poles and no zeros. So this is like this, -2 and -1. Again, we have to find this because there are two roots. This will not be on the real axis. This will be on the real axis, this part. So fine. And then we have to find the asymptote. So we'll try to find the asymptote. Here it was 180 degree. Let us see what is it is here. So -1, -1, -2 by 3. This is the centroid. What does it give? -5 by 3. Somewhat here. Yes. Is my voice not coming? Am I audible now? Or it is still breaking? Okay, thank you. Fine. So we have got the centroid and we have to find the asymptotic angle. So we'll say this is 2k plus 1 by 180 by 3. And this k goes from 1 to 0, 1. Okay. So this will be like 60 degree and then 180 degree in this angle. So now we know that this pole will proceed like this, and these two poles have to break away. So it will break away and move along the asymptote. So for this is the root locus. Now if you see this one, it has two roots, -1, -2. So there are two roots at -2. So we can say, okay, this axis is in the root locus because there is one right half, like right 0, like one pole in the right of this part of the real axis. And if you see this part of the real axis, then again there are three poles. So this is also in the root locus. Now we have to see that there are three poles. So these three will proceed to this asymptotes. So we'll find this one. Now the centroid will change. So what will be the centroid? -2, -2, -1 by, this is 4. Okay. And this is -5 by 3. This would again be somewhat like this. And then we have this asymptotes, which will be again this one same because like for this angle criteria, we just need the n like number of poles and number of zeros. So this will be like this only. So one of the pole here, it is going to infinity along this. Other pole is coming toward this, and this pole is also coming in this side. So this pole is going towards this one. So that means from some point here, it will break away. So we'll have to find some breakaway point, which can get by dk by dx. So we'll just see, since this is the, where was it? This is the function. And we can find the, a characteristic equation that will be s plus 2 whole square s plus 1 plus k equal to 0, and then k will be minus, this will go this side, so it will be minus, and this equation polynomial in s. And if we try to find out, we'll get some value which will be here, and from this point these two poles will evolve and will proceed through like along the asymptote. Okay, so this whole thing, one is going like this, another is going like. So from there we can say, okay, for this one, this is the root locus. Okay, so what we got for first figure, like b is the, in this two, b is the transfer function, like open loop transfer function. Then, like, okay, fine, you understood anyway. Fine, so we'll proceed to next question. So this is the next one, and it says that we have to find valid root locus plot. So if we see plot 1, does this seem valid? What do we know about root locus plot? That this should be symmetric about the real axis. If we see this one, so if it is like this, then it should also have one part of root locus which should be symmetric to this one, like this. But it's not there, so this is not a correct root locus. Then we have the second one, 2 zeros, 2 poles, and it says that, okay, here there are 2 poles, and this axis is in the root locus, obviously, because there is odd number of zeros in that side of real axis, so this will be on the, like, in the root locus, and this is kind of a break-in point, converges to two roots converging to two poles, like, sorry, 2 poles converging to 2 zeros. Okay, so this one is correct one. Then we have this. So if we see this, we have these 2 poles, 1 pole, 1 zero. Now these 2 poles, there is a breakaway point, it is going here, but first we have to see that, okay, real axis and what are the part of real axis that will be in root locus. So this part will be in root locus because there is odd number of pole zeros in the right. Now this part will not be, this part will be, but for this part it will not be on the root locus because there are total number is 4. So 3 poles, 1 zero. So that means this is not a correct or valid root locus plot. Now we see this one. So there are 3 poles, no zeros. We see real axis. So this one obviously will be on the root locus because there is 1 pole to the right of this, and this one will also be. And since there are 3 poles, no zeros, so these 3 will tend to infinity, which is happening. Therefore, this is correct or a valid root locus. Now the system we don't know, but since we know the basic steps and all, so we can say, like, identify which one is valid or not. Okay, so this is about this question. Now we proceed to this one. So this is a unity feedback system with this forward transfer function, which is k s plus 5, s minus 1, s minus 2. It says that root locus consists of a circle. Okay, so root locus is consisting of a circle. Then we have to find the center of the circle and diameter of the circle. So first, let us see if this consists circle. So we have this sigma j omega and 2 poles, 1 and 2. There's 1 0, which is minus 5. So what do you expect? This one would be on the root locus. This should also be on root locus. Since these poles are coming, this will break away. And then here, so there will be some breaking point. So it will evolve like this. This one. So this one, rough, like approximately this type of thing. And it is saying, okay, this is a circle. So we'll now try to find, because this is a circle and this is in which axis? Sigma and j omega. So we'll try to find out in terms of sigma and omega so that we can find the circle equation. So it will be like sigma minus a sigma minus a whole square plus omega minus b whole square is equal to r square. So this will be the equation of a circle. We know this is the equation of a circle. So let us see, for this root locus, there is this angle criteria. So we say that this angle made at any point by all these should be plus minus 180 2k plus 1. So we'll say, suppose this point is S. So angle contribution by these three should add to 180 plus 1. So this will be S plus 5. So this is minus 5. And then angle of S minus 1. So there is 4. So this will be negative. This will go to 2k plus 1, 180 degree. Okay. So now what is the angle? We can write it as tan inverse. This is sigma plus j omega. This is suppose sigma plus j omega. So this will be omega by sigma plus 5 minus tan inverse. This will be omega by sigma minus 1, because this will go to sigma plus j omega. So this 2 will form the real part and this will form the imaginary part. So from there we can find the angle. Tan inverse omega by sigma minus 2, which is plus minus. Okay. So what can we write about this? So suppose we have this one. It T plus tan inverse omega by sigma minus 2. So tan inverse A minus tan inverse B, we can simplify this. So we can write it tan inverse A minus B by 1 plus AB. If we simplify this one, we get tan inverse minus 6 omega by sigma minus 1 plus omega square. This will be equal to now if we take tan on both sides, so this will be minus sigma omega by sigma plus 5. Now tan this angle. So if we see plot of tan, it's like this one. So minus 90 to 90, it approaches infinity at 90, and 180, like any multiple of 180, you can say this will be 0. So this will go to 0. Since this one tan a plus b, so we have to apply accordingly, and we'll simplify this to 2. So I think tan a Okay, so you can check this one. This is a relation, I think. But if you simplify this, so you'll get this one. And further simplifying this, you'll get omega sigma plus 5 square plus omega square minus 42 equals 0. So what does this mean? This means omega equal to 0 and sigma plus 5 square plus omega square equal to 42. Now, so from there we can see this is the equation of circle. That means the center is sigma equal to minus 5 and omega equal to 0. And what is the radius? It is root under 42 because this is r square. So it says that what is the center of circle? So it will be minus 5 and 0. And then diameter of circle, since we have got the radius, which is root under 42, so this will be 2 into root 42. Okay, now you can multiply this and get it in decimal. So what would be the value? 2 into 42, root 40. This is 40, 12.96. Okay, approximately in 12.98. Okay, so this is one thing. Like now we'll see. Now it says that, okay, this is the root locus and we have found out what is the center and all those. So this is one thing that we have done, and basically we requires just for our analysis purpose, we don't go into that deep much, but okay, we want to see the depth in depth, then okay, we do all these analysis, but let us see. So if we can find this plot using our locus command, whether we are getting same kind of thing or not. So this is the system. So we have earlier made a system. Let us clear all those variables. And we have s plus 5, s minus 1, s minus 2. So z equal to minus 5 and p equal to 1, 2. Now we say that we want a system. Okay. Z comma P comma 1 because gain is 1 and it will vary accordingly for root locus. So we get this system. Okay, so now we'll find the root locus of this system. So we can see, okay, this is a circle, which we are saying that, okay, root locus consists of a circle. So this we can see from the root locus command also. Now it is saying that what value of k can we find zeta equal to 0.5. So what will be the gain? So what will be the zeta equal to 0.5? There will be some line like this. It is crossing through an origin and it will cross the root locus at this point, and this cos theta will be equal to 0.5. So that is one way that we can do. We can plot a line with that angle and do this, or we can do this using the characteristic equation. So we have the characteristic equation, which is s plus 1, s minus 2 plus k, s plus 5. So this is g. So we have s minus 1, s minus 2 plus k, s plus 5 equal to 0. So if we simplify this, we'll get s square plus k minus 3s plus 5k plus 2 equal to 0. Now it is saying this is a second order polynomial, like you can say. So we can equate this with a second order characteristic, like a standard system that we have seen, that is s square plus 2 zeta omega n s plus omega n square. So from there we know that zeta is 0.5, and then we have to find the value of k. So that means this is s square plus omega n s plus omega n square. Now k minus 3 is equal to omega n. We'll just equate these two. And 5k plus 2 is equal to omega n square. If we equate this to 5k plus 2, from there we'll get the value that is 10.32 and 0.678. Okay. Now for this value of the k, root is in right half plane. So we are not concerned about this. This value of k at which we get the zeta equal to 0.5. So this is 10.32. Okay. We'll go to next question. And it says that this is one of the system, and here alpha is the varying parameter. So what is the center of asymptote? Basically, earlier we had seen if we vary k, what is the root locus? Like how the root locus is there for the closed loop poles. But when there is some other parameter, like here it is alpha, then what is the root locus? So for this, ultimately, like what we are trying to do, we are trying to satisfy the angle and magnitude criteria of this characteristic equation. So we have this GS and we have HS equal to 1 and GS which is given like this. Then we can find the characteristic equation, which is H1 plus GH. 1 plus alpha minus 1 S plus alpha minus 2 by S plus 1 S plus 2. Okay, so this is equal to 0. We get S plus 1, S plus 2, plus alpha minus 1, S plus alpha minus 2 equal to 0. Now what we do? We simplify this one and we get S square plus 2S plus alpha S plus 1 equal to 0. So we can write this also as 1 plus alpha s plus 1 s squared plus 2s. This is equal to 0. So this is in a form like 1 plus kg, where k is outside of this equation and g is this one. So from there, considering that this is the GH, so this is the GH and this is the K in terms of, in place of K, this is alpha. So from there, we can find the center of asymptotes, and this will be sum of real part of poles, which is there is two poles 0 and -2 and 1 0, which is -1. So 0 -2 minus -1 by 2 minus 1. So this will give us -1. So this is the centroid of the asymptote. Okay. So correspondingly, we can also plot the root locus of this one. So if we see, this is sigma j omega. We have one root at s equal to 0. And we can say one pole at this one and one pole at -2, 1 0 at -1. So this axis would be in the root locus. This would also be in root locus. Since these two, like there are three poles and no zeros, so these three will tends to infinity. Or I have missed. Okay, I have misinterpreted. This is the 0 and this is the pole. So there is one 0 and two poles. And this is on the axis. So this pole is reaching towards this 0 and this pole is reaching towards the infinity. So this will be the root locus of this system. Okay, so we have done this one. We can also plot this root locus. Again, the same thing, R locus command you have to apply, you'll get this. Any doubt up till now? Okay, fine. So if you don't have any doubt, then we can conclude this session and we will meet next week. Thank you.